Permanent magnets are an important part of life. For example, the Earth itself is one such magnet. But where do permanent magnets get their magnetic field? Well, they get a smidge of it from the movements of electrons around the nucleus, but they get a vast majority of it from an attribute electrons have called spin. Now, electrons aren't the only particles with spin, but electrons are the ones that help cause permanent magnetism, so we'll focus on these. What is spin? Spin is a part of quantum mechanics, and because it's a property of subatomic particles, there's nothing in the observable world that can help us visualize it. In order to understand it, we have to examine its effects. Spin was first identified via the Stern-Gerlach experiment, which looks like this. The two ends are comprised of magnets of unequal strength. If you were to shoot a beam of particles through these two magnets, due to the interactions between the magnetic field generated by the moving particle and the magnetic field already there, you would end up with two beams from your initial beam, one going up and one going down. Before we knew about electron spin, it made sense to think that if you were to alter the experiment by shooting electrons through the two magnets, the beam would just pass straight through, unaffected, just as a beam of particles without any magnetic field would. What actually happens, though, is that the electrons separate out in a similar fashion to that of a rotating charged particle. This means that electrons must have a magnetic field analogous to that of the rotating charged particle. We say that this magnetic field is caused by an electron's spin. The similarities between the electrons and the rotating charged particles is how spin gets its name. Particles like electrons split into two groups when put through this apparatus, so we call these two groups spin up and spin down. Despite the word spin, an electron is not actually spinning. We know this because the rotating charged particle's magnetic field is due to the particle's size and the particle's speed. The faster it's moving and the larger it is, the stronger the field around it. The magnetic field around an electron is so strong that, given that an electron is essentially a point object, the surface of the electron would have to be spinning at faster than the speed of light, which we know is not possible. So that eliminates that possibility. Right now, we're still not exactly sure what causes spin, so we put it down as intrinsic angular momentum. This essentially means that the electron acts like it's spinning even though it's not. So what does this mean for permanent magnets? Well, from an atomic to a molecular to a regional standpoint, valence electrons all have to be pointing either spin up or spin down, so that their magnetic moments don't cancel one another out. Since spin is additive, the magnetic field of the entire magnet will equal the sum of all of the magnetic moments from each electron's spin. This is what makes a permanent magnet a permanent magnet. Now, the question we get to pursue is, what are the bounds and properties of spin that we have not even begun to consider?